Yeah, so welcome everybody. This is actually my first webinar, so let's see how this goes. We are going to record this webinar to also make it available for people who cannot make it at this time. So the whole show should take about 1 hour, and yeah, so feel free to raise your hand for questions at any point in time. We can let's try to do it this way. If we find that there are too many questions and we're not making enough progress in the talk, we'll maybe stop the questions during the presentation and have them afterwards. Yeah, all right. So this webinar is about Apache Flink SQL. Flink's SQL API for unified batch and stream processing. We are going to discuss what does it mean to be a unified API for batch and streaming. How does it work to run SQL queries on streams? We're going to have a bit of an interactive session. Like I'm going to show you how to use Flink's SQL CLI client to run queries on a Kafka topic with Apache Flink, and yeah, give a brief outlook of what's coming next. A few words about myself. Yeah, I'm a Apache Flink PMC member. I've been contributing to Apache Flink basically since the first day when it started as an academic research project at Technische Universität Berlin. And for the past years, I've been focusing on Flink's relational APIs, namely SQL and the so-called table API. I'm also currently writing a book called Stream Processing with Apache Flink for O'Reilly, which hopefully is going to be released in the next months. So let's start with a quick recap of what Apache Flink is. Apache Flink is a distributed system for stream processing. Its main purpose is to do stateful computations over streams, and by stream processing we basically mean the whole spectrum of stream processing, starting with bounded streams at the very batchy side, so to say, going over to streaming analytics, and also event-driven applications. So applications that react on individual events, apply some business logic, and then emit other events or communicate with other systems in other ways. Flink is a system that performs many computations in memory and is therefore fast. As I said, it's a distributed system, so it's meant to scale out, and it scales to very large amounts of compute resources. We've Flink users who run streaming applications on thousands of cores. It's fault tolerant, so as a distributed system, this is like one of the core properties that you want from a distributed system. It is prevents or provides exactly once state consistency guarantees. It supports event time processing, which is important if your data doesn't arrive in order. Yeah, and can handle very large application state, so up to a couple of terabytes. Flink is very well integrated in the ecosystem, in the big data ecosystem. So we have connectors to quite a few systems that are commonly used, like Apache Kafka, Kinesis, relational database systems, Cassandra, Elasticsearch, and so on. Flink runs on different resource managers, including Kubernetes, Yarn, Mesos, and can use storage systems like HDFS, S3, or NFS file systems. So Flink runs at quite a few companies. Like these are a few of them that have notable use cases. So Uber, for instance, developed an in-house platform based on Flink SQL. basically providing a SQL interface for their data engineers and analysts to run SQL queries on data streams. Netflix runs Flink at a very large scale. Also as a service for their developers. Alibaba is one of the biggest users of Apache Flink, and quite a few banks are using Apache Flink, for instance, for fraud detection or also master data management. So those four were just a few of the users. So this is basically the a couple of companies who are using Flink as well. And all of them have talked about the use cases at Flink Forward. So coming back to Apache Flink and its APIs. So Flink provides basically 3 APIs that are that serve different needs because they're on different levels of expressiveness and conciseness. So at the lowest level, there's the process function API, which is which provides the ways for users or for developers to handle time and state in Apache Flink, which are like the core ingredients for stream processing. And these functions are typically used when you develop event-driven applications. So whenever you have to react on individual events, then often process functions are used because they're quite flexible. On a bit higher API level, there's the data stream API, which provides building blocks for operations that are commonly used for stream processing, such as windows or a sync operator that sends asynchronous requests to external data stores and so on. And finally, on top, there's like the table API and SQL, like Flink's relational APIs, which have the highest abstraction and make it very, very easy to perform analytical tasks on data streams and data sets. So, of course, we're going to talk about the top layer here on about the SQL part. So, Flink's relational APIs basically are based on ANSI SQL, so we're not using some kind of streaming specific dialect or any kind of like special dialect, but instead trying to stick to the SQL standard as close as possible. So the query that we show here as an example should be familiar to most of you. So it's basically a query that reads from some kind of a clicks table. It groups by the user and then counts how many URLs each user has clicked on. If we express the same query in the table API, you see it looks a little bit different. So the table API is a so-called link style API. Link means language integrated queries. This is a concept that was introduced by Microsoft in their .NET frameworks. And the idea is to not embed a query in a program by just specifying it as a string, as you would do usually for SQL, but instead using methods and objects of the programming language to specify the query. This is what you see here is basically you're starting with some kind of table environment. You're calling a scan method, which basically scans the clicks table that has been registered in the environment before. Then you do group by and select. And if you look closely at the query, you basically see that it is somehow like inverted to the SQL statement. And yeah, so some people find that easier to read because it like flows you defining the query in steps as they're like naturally applied on a table. But nonetheless, both queries are specifying exactly the same query here. And both are also like unified APIs for batch and stream processing. And that basically means that both of these queries can be applied or provide or compute exactly the same result, regardless whether you apply them on a batch of data, on a static data set, or on a stream of data. given that the batch and the stream both provide the same data. So let's look a little bit like how does it work? How does the query translation look like in Apache Flink? So we have those two queries here on the left and the right hand side, and this is basically how Flink's translation framework looks like. It's based on Apache CLIENT-DETACHED, which is a framework or a framework that includes a SQL parser and validator, and also an optimizer that can be customized by providing optimization rules. And both the table API query and the SQL query are, when they're specified, they're translated into the same representation that is right in the middle here. It's the scale-set logical plan. So, and at this level, both queries look exactly the same. And from this logical plan, now this logical plan is then given into the optimizer, which optimizes the query depending on whether the underlying table, like the clicks table, is a static data set or a stream. Depending on this, on the properties of the source table, either the data set optimization rules are used to translate into a batch execution, or the data stream queries rules are used to translate into a data stream job. So you can basically like go from a table API query to a data stream job or to a data set job, and the same also for a SQL query. And yeah, as I said, basically which optimization set of optimization rules Flink uses depends on whether the input data is bounded or unbounded. So what now if we want to apply this query on a file of data, or on a file, basically a static data set? Well, in that case, we have this file with our click data. We would just read this data, we would somehow like pipe it into the query or the query processor, and then we would get a static result for that. So in this case, like the input data is read at once, all the data is read, it's all given into the query, and also the result is produced at once. So this is basically as you would expect it from any database system, right? If CLIENT-DETACHED is now a stream, it's a little bit different, because if you want to read this data as a stream, the data is probably not there yet, right? It arrives over time. So again, we have some kind of schema for the data. Like the data needs to have some schema, just like a static data set. And then the data arrives over time, and as soon as the first record arrives, it is forwarded into the query, and the query then computes the result. So if we get the first line here, the first record where the user is Mary, we pipe that into the query, and as a result, we have a table where we have one result row where the user is Mary and the count is 1. And if now more data arrives, the query continuously updates the result. So we get another row for Bob, so we add another row to the result. If we now get a new row for Mary, the count for the row with the user Mary is updated, and so on. So basically, the result is updated as more and more data arrives. So the input data is continuously read, and the result is also continuously updated. However, what is important here is that the result is in both cases exactly the same. So it does not matter whether we read the data completely from a file, or whether we read the data as a stream, like one by one, and incrementally computed the result. So why is it important to have this batch streaming unification? Well, that's for a couple of reasons. First of all, it's of course a usability issue. So if there is just ANSI SQL syntax, that means that there is no special stream SQL syntax that that you would need to learn, you can just use the regular SQL that you learned, and there's nothing special, no special keywords to learn here. And what's also important is that the semantics are of course the same, right? You could also say, okay, I'm using the same keywords, but then due to for some reason, I don't compute exactly the same results as I would for batch query, just because the data is incrementally arriving. So we don't think that is that this is a good approach. So we say, okay, syntax and semantics should be exactly the same, regardless of whether the data arrives over time from a stream or whether all data is present and is bounded. It's also important for the portability of a query, so you can run the same query on bounded or unbounded data. So this could be helpful if you want to test a query on some kind of bounded data set and then later apply it in production on a stream of data. You can run the same query on recorded data, on real-time data, and both of these properties are important if you want to do things like bootstrapping the state of the query, or also backfilling results. So, for instance, if you have a system that had an outage for some reason, you can always run the query that usually runs in production or data stream. You can take the same query and run it on some kind of recorded data later on to just recompute the results that were not computed for some reason. So now the question is, like, how does it actually work to apply these? To run a query or evaluate a query incrementally on a stream of data. And this is actually something that database systems are already doing. So there is this concept of this feature of materialized views in database systems. And these views are very similar to regular views. So you just specify a view. But instead of like the regular virtual views, which are like computed when you access them, these materialized views are pre-computed, and the result is stored on a disk at the memory. So materialized views are typically used to speed up analytical queries. So if you run the same query, or if you run similar queries that would leverage like a common sub query, you can basically make this sub query a materialized view, and then this result would not need to be recomputed whenever you run a query on this. So database optimizers then, when you have a materialized view, a database optimizer would figure out whether this view is applicable to your query and then use the view instead of recomputing the result again. However, materialized views, of course, need to be updated when the base table is changed, right? So if you want the queries to always provide or if you want the materialized view to be used to speed up your query, you also want the data of the materialized view always to be up to date, right? So as soon as the base tables change, these changes need to be somehow incorporated into the view. And this maintenance of a materialized view is very similar to applying SQL on a stream of data. So you can think of it as follows. So all the changes that are happening on the base tables, it's like a stream of changes that are applied to the base table. And then the view definition query, the query that defines the view, is the continuous streaming query that takes all these changes that happen on the base tables and turn them into changes that are applied on the materialized view. And this way, database systems are currently or somehow already running SQL queries on streams of changes. So in Flink we have the concept of continuous queries, and these queries are running on dynamic tables. Dynamic tables are basically, as the name suggests, are tables that are changing over time. So they can just receive more data. They can also change the data that they already have. They can also lose data, or data can be deleted from these tables. And in principle, you have like a table that is like a regular static table at some point in time. But over time, this table, like the content of this table evolves, and then you have like this dynamic table. when you specify a query in such a dynamic table, the result is also is a new dynamic table. And as changes are applied to the input of a query, the query will then look at these changes and apply them on the results table. So basically, just like what I said before, just like a view maintenance in a relational database system. So now the question is basically, how can we, coming from a streaming background, now the question is like, how can we turn such a stream into a dynamic table? And there is a couple of ways to do that. Like the easiest way is like the so-called append conversion. So if you have a stream of data and your table, you can model your table such that each record that is arriving from the stream is just appended to the input table, right? So in this way, basically the dynamic table will always grow because you're just appending your records to the table, and there are no deletes and no updates. So as more data arrives, the table grows, and since if you assume like the stream is like infinite, also the size of the table is infinite. Another conversion is the abstract conversion. In this case, the resulting table the table that you're representing needs to have a primary key, a unique attribute. When new records arrive from the stream, you're basically the stream. Sorry, then when a new record arrives from the stream, the record will either be appended to the table if the key attribute of this record was not present in the table already. But if the table has already a record with this key, then it will update the record with that key. So this is like a abstract conversion. So a new record is either inserted, like appended, or updating a record if the key is already present in the table. And finally, there is also like a so-called changelog conversion, where each record that arrives has a flag what kind of change it is, whether it is like an insertion or a deletion, and based on that flag, we insert records into the dynamic table or remove records from the dynamic table. So Flink in Flink 1.7, like the current version of Apache Flink, already supports quite a few SQL operations on streaming and batch data. So of course we support the very easy selection projection filter queries, select from where. We also support group by queries with having on like non-windowed aggregations. These are like the ones as we saw in the example. We simply say group by user, and there is no window involved in this aggregation, and we're basically computing an aggregate per grouping key basically. Flink also supports group by so-called tumble hop and session windows. We're going to see an example like how that looks like later on. They also support for different kinds of joins. There are so-called time window joins, basically where you have two streams of data, and you say from this I want to join every record from this side with records from the other side that fall into a specific window. So for instance, if I want to join it with everything that arrived 10 minutes earlier and 1 hour later. So, and then you can basically use this definition to define a window for the join condition that you want to apply. Flink also supports various kinds of user-defined functions, so Scala functions, aggregation functions, and table value functions. There's a couple of things that are only supported in streaming, like over windows and inner joins with time version tables. Something that we're quite excited about is support for the match recognize clause, which is something, a feature that was just recently added to the SQL standard in SQL 2016. And this match recognize clause is a way to specify patterns on tables. So with this feature, we can express complex event processing or pattern matching like queries in SQL. And this is really exciting because you can mix and match like pattern matching part with the analytics part. So you could look for specific patterns in your data stream and then apply some analytics on that, like how often did that pattern appear within a specific amount of time, or you can first pre-aggregate your data and then apply patterns later on this aggregated stream. So this is something that is really nice. All right. So what kinds of things can you actually implement with like the tools that Apache Flink provides for the relational APIs? First of all, like the most common use case is to use SQL for data pipelines, like just moving data from one stream to another, filtering out records, transforming them, like the simple select from where queries, maybe with some kind of window aggregations. This is like a very common use case. You can of course also use it for more involved analytics things where you join data together. You apply continuous analytics on some kind of joint data streams, for instance. But you can also use it to power dashboards, for instance. So you can have a stream of data, you apply a continuous query on the stream of data. It generates some kind of like a materialized view, a table that is updating as more data arrives from this data stream. And then you can materialize this view or this dynamic table. You can write that into, for instance, a relational database or key value store, then have a dashboard accessing the data. And as soon as data arrives from the stream, the query will process it, will update the table in Cassandra, for instance, or MySQL or whatever, and then the dashboard will automatically always fetch the latest results from the data store. So there's quite a few nice use cases that you can address with streaming SQL. All right, so now we've talked about like what Flink SQL can do. We talked about like how it works, but how can you as a developer actually use Flink SQL? There are two ways to do that with Flink right now. So the first one is to embed SQL queries in regular like Java Scala applications. The table API and SQL are tightly integrated with Flink's dataset and data stream APIs. So you can easily convert a data stream into a table and then run relational operations of the table and also convert it back to a data stream. Same works for data sets. And this way you can like mix and match the different APIs with each other. You can then simply package your application as you would like a regular Flink application as a Java file and submit it. So all of this basically works exactly as you would do for a regular Flink Java or Scala application. This is very nice, like from an operational point of view, but like from a user point of view, like usually when you're using SQL, you don't want to step into like implementing a Java class. So there's also a command line client that Flink provides since a few releases, and with this command line client, you can run queries in an interactive mode. So basically, to try your queries and see like use this CLI client to develop the queries that you're looking for. And later, you can also submit the queries in a detached mode. Basically, just specify the query, send it to a Flink cluster, and then Flink will start the query and keep it running, even if you like later on exit the CLI client. So this is a way to just send off a Flink job specified as a SQL query. All right, so how does this SQL client look like? So first of all, the SQL client has some kind of catalog. This is currently being implemented with a configuration file. So you would specify in the configuration file what kind of tables or source and sync tables the catalog can, or you can access with your SQL queries. So this can be a Kafka topic that you specify as a table, as input table and output table. This can also be like a directory where you want to write data out to. So all these tables are currently, like as I said, specified in a configuration file. Part of the CLI client is also the optimizer and a so-called result server. So when we when you start the CLI client, you would like enter a query and submit it through the basically enter it in the command line client and execute it. And when this happens, the optimizer will take the query, will optimize it. It will compile a Flink job from that, submit the query job to the Flink cluster that was also like configured in the catalog in the configuration. And when the query is received by the Flink cluster, it would then the Flink cluster would read the data from the tables that were used in the query, serve the results back to the result server, and then the results would be served on the screen. Basically, you would then basically see how the query is being evaluated on the data stream. So I've prepared a little demo for this. So we're going to use these New York taxi rights data set. So this is a public data set about taxi rights in New York City. And what we did for the demo is we basically modified the data a little bit, and we are ingesting it into a Kafka topic. And on this Kafka topic, we're going to run some queries. So the whole setup is in a Docker Compose setup. So just the font size maybe a little bit. So we are I'm starting now like a Docker Compose setup that starts a couple of containers. You see we have some kind of job manager, Flink job manager, we have a Flink task manager, we have a Kafka, a Zookeeper cluster, we have an Elasticsearch container, and a container running the SQL client. Now, if we step into the SQL client container, we can start the SQL client. And you see we have a very nice squirrel here that is welcoming you. And on the CLI client, we can now run queries. We can first check what tables are there. And we say show tables. And we see that we have 3 tables here. We have the taxi rights table, which is our source table where all the taxi ride data is coming from. And we have 2 sync tables here, a table like called area accounts, which is backed by an Elasticsearch index, and this 10 minutes passenger count sync, which is backed by another Kafka topic. So we can now see how the taxi rights table looks like. You see it has exactly like the fields that I've that were listed before. So we have some kind of a ID for a ride. We have a taxi ID for the car, for the taxi. We have an ID for the driver. We have a flag that says whether this is a start event or an end event. So each taxi ride is represented as 2 events. One event that is set out when the taxi ride starts, and another event that is set out when the taxi ride ends. We have the longitude where the event happened. So for the start event, this is like the pickup location, longitude and latitude. So this is the pickup location or the drop-off location, depending on whether the start flag is true or false. We have also have the time when the time when the event happened and the number of passengers that were on this ride. So we can now like run a very simple query just to select the whole table and just see how the content looks like. This is very simple, of course, but basically see that the query is now submitted in the background to the Apache Flink cluster, and you see like how the events are now being read from the Kafka topic. You can also see connect to the Flink dashboard that is now executing the query. You see here that we have this this query select star from taxi rides. It's a query that is all collapsed into a single operator here, because like all the operations can be chained, and we should see in a few seconds like how yeah. No, there is no statistics because it's all collapsed into one node. Anyway, so we can now quit the job here on the CLI, and you'll also see that now the job here is mentioned as cancelled. So if you now want to run like a little bit more complex query that is similar to our initial example, like a simple group by query, we can do this with this query here. This query is a query that reads all the taxi rides, filters on is start, so we are interested in start events. And we want to group by passenger count to basically get like a histogram of how the number of passengers are distributed for rides in New York City. And if we run this query now, we see that we have like 6 different passenger counts here. Like the maximum number of passengers in these rides is apparently 6. And you see that as more and more data is received, the numbers here are increasing. So like most people, most of the time, like most taxi rides are only serving like single passenger, as we would expect. And then like with growing number of passengers, the number of rides gets less. So again, this query is also running here in is shown on the web interface, and you see here like the number of records that were sent out from the source node and were received by the aggregation and sync node. All right, let's quit this query. So this is like a simple aggregation that is like updating the result as more and more data is arrived. But a very common operation for in streaming applications and streaming analytics is also like to perform computations in like so-called windows. So you maybe want to have like a count you want to count every 5 minutes for each area the number of departing and arriving taxis. So we have this query here that is doing exactly that. So we have like a sub query here, where we just select the time when an event took place, the flag, whether it is like a start event or an end event, because we're distinguishing here departing and arriving taxis. And we're using a function here to area ID, which is a user-defined Scala function that takes the longitude and latitude and then computes for this location a sort of like area or cell ID. Like we kind of like transform the longitude and latitude in a net of or in a mesh of cells of 100 by 100 meters. In this way, we can basically also aggregate later on this data. So we get from the subquery, we get the time, we get the start flag and the area ID, and then we group on the area because we want to group per area. We want to group on this start because we want to know like the number of departing and arriving taxis. And then we're using this tumble function here, which is like a special built-in function that basically generates 5-minute windows based on the row time of the event. Records are assigned to that window in which the row time basically falls. And then we select we group on that and select the area ID at the start flag. We select the end timestamp of the window. So if we have like a window from 12 o'clock to 12:05, then 12:05 would be returned from this function here. And then we have a count aggregation to just count how many events we've seen for this area, start flag and window. So if we now use this query here and run it, again the query is optimized and now sent to the cluster. We basically see now here the results. So this is the area ID. This is the start flag. False means this is like counting arriving taxis, and true means it counts departing taxis. This is the timestamp of the end window. We've seen like before we had 1:15, now it's 1:20, and the next one will be 1:25. And the results are not like appearing all at once, but over time, because we're piping the data into the Kafka topic, basically while the demo is running. We don't have like a pre-populated Kafka topic here, but like to simulate like a true streaming case, we're just piping data in as we have this demo running. We're piping it a little bit faster, so we don't have to wait 5 minutes here. We're piping it in like I think in 10x, so 5 minutes of data are pushed into Kafka within 30 seconds. So every 30 seconds, we're going to see like a new result or new results for the next 5 minutes here. And we can now like basically keep these continuous processing, continuous analytics running until we run out of data in Kafka. Again, we see the query here. Again, it's like two simple nodes, and you basically see here some stats for the job that we are running. All right, so I'm gonna stop this query here and go back to the slides. So this is like the interactive mode that I was talking about. So you can basically run and develop your queries that are evaluated on streaming data, Kafka or Kinesis or whatever. So we're not bound to Kafka. You can basically, if you have like the right connector for your that ingests a table, you can run queries on any kind of data stream. And I was also talking about this detached mode, basically submitting query to a Flink cluster and then not like receiving, not displaying the results, but instead like sending out the query that ingests data from some data source and writes it to another. And this is exactly this case. So in this case, we have again the same CLI client. Again, we have some kind of catalog here that defines source tables and sync tables. We write a query here. And if you look at the query, it says insert into sync table and then select from where query, like a simple select query. This query will basically write the results of the select query into the sync table. And when we submit this query, the CLI client will optimize it, will translate it into a Flink job, submit it to the Flink cluster, and then the Flink cluster will ingest the data from the source tables and write it back into the sync table. And instead of feeding back a result to the CLI, it just submits like a job ID and a cluster ID that basically tells you, okay, we have started this job on this cluster, and it's running now. So we can try to do this here. For instance, like try to like do a simple demo for writing some data into Elasticsearch. So if we have like this taxi rights data, we can now have a simple query here that basically inserts into these area counts sync table that is backed by an Elasticsearch index that I shown before. And the query here basically just groups by the area ID and counts how many departing rights were there per area. So this is not like a time windowed aggregation that basically computes a new aggregate for every time interval, as we've seen before with the tumbling window query. But instead, this is like a standing query that updates continuously, increments the counts for the areas where taxi rights are part. If we now, and you see here it says insert into, so this is like a detached query. If we now submit this, you see that we just get back a cluster ID and a job ID here, and the CLI client now is basically done. It just submitted the query. Does not have to show any results. But if we go back to the Flink dashboard, we see that also this query was received, and it is writing data into Elasticsearch. And you can see this. So this is like the REST interface of Elasticsearch. If you look here at the counts, if we now refresh like this query, then the counts will change and will basically this basically shows that more data is written into Elasticsearch. Let me see. We can also show some example data here for the Elasticsearch index. So for instance, here we have we are looking for a particular area ID, and yeah, basically see the data here. It says area ID 49791, and it has a count of 114. And if you now reload, it's 118. So in the meantime, 4 writes have departed from this area. So if we now want to stop this query, we cannot do it from the client, but instead we can do it from the web interface here and just say cancel, and then also this job will be canceled and gonna be stopped. All right, so this is like the current state of what Flink SQL can provide in Apache Flink 1.7. However, there's a lot of more things to come. Not sure if you're read the news. So Alibaba has decided to contribute many features of its Flink fork called Blink back to Apache Flink. And part of this contribution will be major improvements for the relational APIs like SQL and the table API. This includes better coverage for SQL features. In fact, Blink has full support for TPCDS, which is a common benchmark for decision support queries, like heavy analytical queries. I think the benchmark consists of 99 queries, and Blink supports all of them. It also has much better performance to what Flink provides right now, mostly on the batch part. And we're also working on improving connectivity for the table API and SQL, meaning that we are working on support or better support for external catalogs, basically being able to access all data that is, for instance, stored in Hive, and also using the Hive meta store to store catalog information. So you don't have to put it in a configuration file, but instead write a DDL statement that is then basically recorded into the external catalog. And from then on, you can use the tables that were basically created or defined and stored in the catalog. There are also plans to improve or extend the scope for the table API in the future. Like this means extending support for user-defined functions, so not only supporting the classical relational user-defined functions, but also something like more generic functions, like reduce functions, map functions, and flatmap functions. And in the future, also support for adding support for machine learning pipelines. And Alibaba also has a big library of machine learning algorithms that they plan to contribute. All right, so that's it. So we talked about like unification of batch and stream processing and why it's important. We've shown that like how Flink tackles this issue. So not having specific streaming syntax, but rather going for ANSI SQL syntax and semantics. Flink SQL solves many of the streaming use cases and batch use cases already. It's used in production at Alibaba, Huawei, Lyft, Uber, and others. You can deploy SQL applications either as an application, as a regular Java Scala application, or via the command line client. And yeah, Apache Flink is an open source project. So if you're using Apache Flink, or you find that you would like to improve things, or you find bugs or whatever, or encounter problems, please feel free to reach out to the mailing list, ask questions, make suggestions for new features, contribute, and yeah, so yeah, that's all that I have prepared for this presentation. Well, not everything. I should say thank you, and also look at this nice cover of the book that we're writing, that me and Bastian are writing. So we're going to be like one of the first books that comes with O'Reilly's new colored covers. So before they had like the monochrome covers, and now it's going to be like nicely colored. I find the school quite cute. And yeah, so with that, we're done. Please let me know your questions. Wait, somebody had a question. Okay, let me see. Oh, there's Q&A. The question is, are you supporting ODBC connections with Flink? Could be used as a source for business intelligence dashboards like Tableau. No, we're not, unfortunately not supporting that. So part of the reason for this is that this works not so well with this concept of streaming, right? If you have like a standing query that continuously updates data, then you basically would need to be able to push data or updates to the receiving side, right? So usually like in ODBC, this is like you're running the query and they get the full result back, right? Whereas if you have a standing query, you would also need to serve updates or basically retract results. You would have to say, hey, this count is not accurate anymore. I have a new update, new count for this. So you need to be able to remove something from the result that you've basically served to the application before. Like one way to go around this is to basically write the data, like the data of the continuous query, into a database, like a MySQL, Postgres, or whatever database. Updating the data in the database, and then have a dashboarding application always going against this database, and always getting the freshest results. But the database would be basically acting as like the connecting part between the continuous query that is updating the data and the dashboard that is always getting the most recent data. Another question here is, are you supporting triggers in the SQL API? No, we're not supporting triggers. So triggers are basically a way to register actions when when certain events are happening, right? So Flink itself is not really a data storage, right? So it's not really meant to write data there. However, I think you could implement that like in some way by having a query that is producing some result into and continues like producing a stream of change, or basically a change log of a result table. And then you could implement a trigger using Flink's data stream API that ingests this change log and then basically clicks on you as whenever the trigger condition would be fulfilled. The next question is regarding non-window join. I'm wondering about how long time state will be maintained. Yes, that's a very good question. So if you want to join two tables and you don't have a window condition, then in order to do that like deterministically and correctly, you need to basically materialize both inputs forever completely. So if one of the inputs is a table that is like append only, just growing over time, this basically means that at some point in time you would run out of resources, basically out of like storage for your storage space for your state. Because the reason why you need to materialize everything is that without a time condition, like every new record could join with the first record that you receive from the other side, and vice versa. So you basically need to, like, in order to have the right semantics, right SQL semantics, you need to remember everything. Flink supports something that we call like state cleanup. So you can define that you want to remove state if it has not been accessed for a certain time. So you can, for instance, say, hey, I want to like do this join, and however, whenever a row has not been accessed, like for a day or so, I want to forget about it. So this basically means that the join that you're running will not be deterministic anymore. You won't get, or you might not get the exact result, because if you remove something and then later on comes something on the other side that would need this, that would have joined with the result, you cannot do the join anymore because the data is gone. However, this is like one way to go around this problem of infinitely growing state. I should mention that, like, for non-window joins, they can still be useful because not all tables are always like append only. So if you have like tables that have like a unique key or primary key, and you're just and the content of the table is just changing, you're continuously updating the rows in the table, you still have like an infinite stream of changes to the tables, but the tables itself, they will not grow because you're just changing data as it that is already in the table. You're basically replacing the data. And if you have like this case that you want to join two tables that are like more or less constant in size, but like updated from a stream, then you can still do this join. You typically will not, well, it really depends on the concrete case, but there's cases where you will not run out of memory, and if like memory might still be slowly growing because like the size of the tables is growing, the size of the tables will also grow if you would like materialize them in a database system. But Flink also supports scaling out of streaming applications. So if you're running out of state at some point, you could scale the application to a larger set of nodes and redistribute the states across more nodes. All right. Any more questions or feedback? I think we're made it almost on time. Yeah, thank you all for joining this like first time webinar for me. It was fun. I hope you learned something here as well. Yeah, stay tuned. And as I said before, if you're using Flink, if you have nice use cases, go and join the Flink community. Thank you, everybody.